Okay, so our speaker is back. Welcome everyone for today's first Quantum Matter Journal Club. Our speaker today is Mr. Yuxuan Zhang, and he's gonna tell us about the symmetry indicator and its relations to band topology. For some non-experts, symmetry indicators and quantum chemistry and topological quantum chemistry or some related works are one of the most important achievements in the field of topological materials. And it has some wide applications in the material science or chemistry. But its theoretical formulation is kind of simple. And let's welcome Yuxuan, and he'll start. Yeah. You can
your camera is on, right?
Camera is not on.
It's not on.
Yeah, I can.
Do you want the camera to be on?
Yeah, it's on now.
Okay, sure. Okay. But I'm not sure if they can see the board or not. But,
yeah, they can see the shared screen.
Okay, I'll start.
Yeah, you can start.
Yeah. Okay. So I'm gonna talk about mainly a paper by Hoi Chun Po, published recently on symmetry indicator. Okay, a symmetry indicator is just a mathematical tool, and I will discuss the physical significance of it and how you can calculate it and apply it. So the whole discussion is about band topology. And before I delve into the mathematical thing, I want to give you some incentive on why we want to talk about this. So we know there are some materials that is topological. For example, there is some quantized response that we can measure for some material. For example, this is a paper published almost 10 years ago by my former PI in UCSB, Andrea, who do some study on electric transport on graphene. So what you're seeing here is when you apply a transverse electric field and a vertical magnetic field, you will see a quantized response of Hall conductivity, which is the conductance in the y direction as compared to the current applied in the x direction. So as you can see here, this black line, I'm not sure if the online person can see it, but this black line is stepwise, which quantize at different values of h over e squared. And this phenomenon is very baffling. And we have a mathematical tool to describe it, which is...
Can I ask a quick question? So, yes, I can see that the black line is stepwise, but what are the units on the y-axis? Because
on the y-axis, h over e squared.
H over e squared. Yeah, but is it in the multiplication of 0.25 or
the conductance is quantized to an integer, but this is resistance, which is 1 over the conductance. Okay. So it is quantized to 1/4, for example.
Okay. But what about the small plateaus below?
The small plateaus here are our x-axis transverse electric resistance.
Okay.
So it is the potential response of a current in the same direction. Basically.
Okay.
Yeah, and this is discovered in graphene a very long time ago.
Okay.
If
you have any questions, just feel free to.
Yeah. Feel free to ask. Like whenever you can stop.
What do the colors represent?
The color is thermal activation.
Okay.
So you can see the black line here is a very low temperature. And as you go higher temperature, this RXX peak gets spread out with thermal activation. And this is actually a sample that I made in my undergrad. this is on the material of a twisted battery graphene, where you have two layers of graphene twist on top of each other with an angle of 1.1 degree, which we call magic angle. And in such configuration, you actually have a flat band which hosts a plethora of different states, like superconductivity. Here is a particular state, which is called quantized anomalous Hall effect, where you don't apply a magnetic field at all, but you get a quantized conductance. Here is h over e squared of the resistance. Okay. Which?
Is that a distance?
Yes, that is a hysteresis. I should, yeah. So how to read this graph? When you sweep your magnetic field from negative to positive, you trace this solid blue line, and when you go back, you trace this dashed line, and with that you have some hysteresis effect with some Berghausen noise, which I'm not gonna go into, but. How we calculate the resistance is the top resistance minus the bottom resistance. The quantized anomalous. But in this case, the Chern number is plus minus. Okay. Next, this is
Particular.
yeah.
This is some at a particular filling.
Yes, in particular, it is 3/4 filling. I believe it's plus 3/4 filling. At that particular filling, there's a split. So I can go into more details on that. Okay, let me twisted battery graphene 101. So there's two symmetries generally present in the battery, which is k to minus k.
You can speak louder. Maybe.
Okay, k to minus k, and maybe they cannot see the board. But yeah. So k to minus k, and I believe sublattice. Yeah, sublattice symmetry. There are 4 Dirac codes for the twisted battery, and it turns out that at 3/4 filling, one of the bands split into Chern +1 and Chern -1. And when you fill to 3/4, you fill one of those Chern bands to have a Chern number plus ±1. But yeah, that is some way. Yeah.
Oh, so if I fill to 3/4, the total Chern number is non-zero.
Yes.
So it spontaneously breaks time reversal symmetry.
Yes, it spontaneously breaks time reversal symmetry. Yes. Okay, we have something to say about this. This is believed to be the first orbital magnet that is discovered. Anyway, I won't go into too much detail on my former experiments, experimental results, but there, aside from Chern number, there are some other topological index that is found, for example, in the topological insulator. I personally am not an expert on this. I like Jingchen. Jingchen can definitely say something about this. But the thing is, we have a well-defined C2 index that can be calculated using a formula that multiplies all the time reversal eigenvalues on distinct k points that respect time reversal symmetry. Yes. I think that is it. Okay. Yes. So in 2D, such a topological insulator, an example would be a quantum spin Hall effect, where you have a spin up copy and a spin down copy with the same Chern number. One with plus Chern number, one with minus Chern number, and if you add those, you get 0 Chern number. So the total system respects time reversal symmetry. But I want to emphasize that it is the inversion symmetry here that is significant, as I will talk later.
Yeah.
The C2 index is protected by the inversion symmetry.
I think we'll have to be careful about the use of inversion or time reversal here. Because I think what you're talking about is the inversion between the upstream and downstream, right? Or no?
So, in the spatial Z direction.
Spatial Z direction?
Yeah, so actually what predicts it is time reversal, but you can use inversion as a symmetry indicator too.
Yeah. So in this case, time reversal and the spatial inversion as Z direction is the same, right?
No.
No?
No. So
Okay.
time reversal flips momentum,
Yeah,
but does not flip X, the position, but inversion flips both.
Okay.
Both momentum and position. And inversion does not flip both. Time
Yeah,
reversal
yeah. That's okay. Yeah.
But maybe we can discuss a bit more later after the talk
Yeah.
on the difference between time reversal and inversion.
So there are, I believe there are a lot of experiments, especially on 3D, for this C2 topological. And okay, so yeah, the paper I'm gonna talk about is about symmetry indicator, which is really a generalization of these Chern numbers and C2 topological index that we discussed in the previous. So the drill of this is, so firstly, you have a constraint that this only describes a system with non-interacting fermions, with no spillover coupling nor time reversal symmetry. But you can relax this constraint of no spillover coupling and time reversal symmetry later. But here, I would give you a band structure example. So I assume you know what band structure is. So you have a translational invariant lattice. So by block theorem, your momentum space band structure will be also periodic. So you have this band structure from minus pi to pi, where all other momentum is ignored, simply because they're related by symmetry. So here I have, yes, for this construction specifically, it is a 1D chain with some band structure where the wave function is either even or odd under the inversion symmetry. I'll talk about that later. Yeah, just keep in mind on these two pictures. Yeah. So why do we want the symmetry indicator? What is the merit of calculating such index? So before physicists and experimentalists want to find some particular material that is topological. So how they would do that is basically experimentalists would try a lot of different materials and see if they're topological or not, to see if there's an index or a Chern number.
Yeah.
And the theorist would try to use first principle to just calculate the band structure and see if there's any topology.
Yeah, a quick comment.
Yes.
So here the topological means the usual topological insulator and topological semi-metals. I think that's the sort of constraints when they consider the theory of symmetry indicator. But that can definitely be like applied to some wider categories of topological materials. But yeah, the original thought was to apply it for all the topological insulators and topological semi-metals.
Okay.
Yeah.
Okay.
Just go ahead.
Yes. So where was I? So yeah. So the merit of using a symmetry indicator is that given we can just calculate the symmetry indicator, which is a generalization of the Z2 index or the Chern number, by symmetry of your lattice, rather than using a very lengthy first principle calculation. And we can predict whether that crystal can host a topology or not, a non-trivial topology or not. And this is the basic why we do this. And how we calculate symmetry indicator relies heavily on the two things that I'm gonna introduce to you, which I want to stress on the distinction. They are very important. So there is what I call an atomic insulator, and we call a band structure. An atomic insulator classifies a phase of the material where all the electrons are localized at a high symmetry point, and there is no entanglement between each other. So it is by definition trivial. But the band structure can describe generally the full information of the band, including the Chern number or the Z2 index. So naturally, the integers that need to classify atomic insulator is a subgroup of the band structure, which I draw here. So here is a typical, assuming you have two kind of parameters to describe the full classification, being mu or n alpha. I'll introduce these later. Why there's you can see that they can be of the same dimension, but the quotient group will give you a C4 classification, a finite ability. And that would be the symmetry indicator that we're going for. And we're going to show that indeed the Z2 index of the topological insulator can be derived from this formula. Okay. So the general procedure is that we're going to calculate BS, which is the band structure, by a mathematical. If you don't know, you can see it as a black box structure called the character table of the irreducible representation. Well, the atomic insulator can be classified by a real space, one near center on the Wyckoff points, localized at this high symmetry point. And then we will calculate the symmetry indicator. So let me give you an example of given a symmetry and we calculate AI and BS. Okay, so this is a very simple example, which is P2. A P2 symmetry is a 2D, two-dimensional symmetry, a wallpaper symmetry, where here shows the unit cells. So the yellow region shows a fundamental domain, which means any other part of the lattice can be uniquely specified by whatever is happening on this yellow region. So you can see there's you can assume there's a translational symmetry, and these red same color squares are identified as the same point. So there are we can see this as a momentum space band structure, and there are 4 distinct points, which all of them hold C2 symmetry. So if you consider if you rotate around this blue square by 180 degrees, it will map to itself. Or same thing goes as for all of the others. This is a lattice in maximum. And to calculate BS, we will need the character table, which is really, you can think of it as the eigenvalue upon acting on the group element of C2. So I've discussed on all these 4 points, they all have C2 symmetry. I want to stress that this is generally not the case. So for some other symmetry group, wallpaper groups, there could be some points that have reduced symmetry from the full. For example, if you have a D4 symmetry, it can be reduced to a Z2 cross Z2 symmetry. But here, because I'm talking about a very simple example, any wave function around this point, for example, around this blue square, for example, can only have eigenvalue on C2 to be 1 or -1. Because if you act C2 twice on your wave function, you will get back to yourself, because C2 only rotate 180 degrees. So naturally, you will have eigenvalue 1 or -1.
What are the A points and B points?
So A, B, and the U are irreducible representation, which basically means how the wave function can be around some points.
Then did you specify which points on the lattice correspond to which EREPs?
No, I haven't specified that. But
Okay.
that is a free parameter. We can specify.
Okay.
So there are 4 points, and each point can choose one of the two irreducible representations. So naturally, there we can see how many integers we need to classify this. It's gonna be Z8, Z to the 8, which means that you need eight integers to classify such band. What are those 8? You may ask. So there are 2 integers on each point. The integers being how many bands of the corresponding irreducible representations are there. So for example, in this band structure that I showed you previously, at this 0 point, this is a 1D example, so it only has 2 high symmetry points, which is 0 and pi. On this 0 point, we have the symmetric wave function to have 3 bands. There are 3 plus signs here. So at that point, this integer is 3. If it's antisymmetric, there's 1 band that is antisymmetric. So there's an integer which is 1.
How do we find the 3 and 1?
It's a free parameter.
Yeah, I mean, where does the 3 and 1 come from? Like, what kind of?
You can have 2 and 2. Just
okay.
Yeah.
We look at what are atomic insulators are possible. So
this is BS.
So you could.
This is a momentum space.
Oh right.
Yeah. So
I see.
So this is BS. Where I'm calculating BS, not AS. But they're very similar.
Okay. Yeah. So So yeah, in BS. So at each isometric point, you could have any number of bands. Like for example, if you consider a 2-band system, then you just need like 2 bands in that point. But if you let's say your system has 8 electrons per unit cell, you're looking at 8 bands.
Yeah.
You need to split it between all of these.
So here we are specifying that we have 4 bands, right? Or
yes, here because the classification is Z to the 8, right? So what I'm saying here is that one integer in that Z to the 8 is 3.
Yeah.
One other integer is 1.
Okay.
I'm sorry, this should be Z to the 2 because there's only 2. Z to the 4th actually. Yes, specified by these 4 integers. So I ignored a very important point, being that what does it mean that this integer to be negative? I'm saying Z, so Z being integer can be negative. This is not the main topic of this talk, but you can extend that into negative integers to what we call what is it?
Fragile.
Fragile topology. If you're interested, yes. Okay, and there's an extra integer beside these points to be new, the total number of bands that you fill. So we aside from these 8 integers, there's a 9th integers of how many bands totally there are, and there's a compatibility relation, being that so in this example, the new is 4. You filled 4 bands, but at this particular high symmetry point, you have 2 integers, which must add to 4. So that is a compatibility relation. For this system, I have 2 compatibility relations. For this system, we have for this system we have 2 compatibility relations. For this system, we have 4 compatibility relations, which is written compactly here as this matrix. So C times n equals to 0 is the full classification, and the full classification can be solved by this. It is exactly the null space, the solution space of Cn equals to 0, and the vectors that spans that null space in this case would be this 5 vector. So really, the full system of BS is specified by 5 integers. The length of these B vectors. Okay. That's how we calculate BS. On the contrary, AI is calculated in the real space picture. So we imagine that you have a square lattice, and there is a localized orbitals on each Wyckoff points, which is a high symmetry point. There are 4 Wyckoff points for the C2Z symmetry, and for each Wyckoff points, you can have eigenvalue 1 or -1 for after you acting on the C2Z symmetry. So there's 2 choices per Wyckoff point, and in total you have 8 vectors for each vector. So the 8 vectors listed here, and if you look closely, they are not linearly independent. So we can reduce the space spanned by those 8 vectors by these 5 vectors. It turns out if you this will span the whole space of AI, and if you compare this AI space to the BS space, you'll find that the first 4 vectors are exactly the same, while the 5th vector is multiplied by 2. So as I've claimed, the symmetry indicator is calculated by BS quotient out AI. That will give you a C2. Give you C2.
What's XBS again?
XBS is the symmetry indicator.
Okay.
Is the obstruction of why you cannot describe everything using an atomic insulator formalism.
Okay, yeah. But the notation is a little.
The extra information encoded in the system.
I think you should label as SYM IND, or just stands for symmetry indicator or something. The XBS is.
Yeah, sure. Okay. I should also use latex. Okay. Anyway, I think you get the point. In this simple example, the symmetry indicator is C2, and you have C2Z symmetry. Remind you. Okay. Why do I make this example, and why is this significant? So it turns out that the parity of the Chern number, which is calculated using these equations. I'm not going to derive this. I'm just going to give it. Is 0 for all AI vectors. So if you plug in the AI vector to here, you'll find that this theta is necessarily 0. But if you plug in the B5, which is the vector of the 5th vector of the BS, you will find that it will give you 1. So the extra information is really the parity of the Chern number.
Yeah, tell me about this, like how.
You can look at the papers. It referenced some other paper, and I didn't look too much into it, but it is established that this is the parity of the Chern number. And you can also check that if you have C3, C4, or C6 symmetry, the symmetry indicator will be respectively C3, C4, and C6, and they are exactly the Chern number modulo n, which is in this case.
Okay, wait a second. So is Z3, Z4, Z6 special, or it only applies to C3, C4, C6? So I mean, the 3, 4, 6, are they special or no?
Are they special? What do you mean? Are they special?
So does Z3, Z4, Z6 apply to all of the CN rotational symmetries, or do they only apply to C3, C4?
In two-dimensional, there are only C2, C3, C4, and C6, corresponding to what is C4 lattice? So okay, C3 lattice is more, it's like a hexagonal lattice.
Oh yeah,
C4,
that can be divided by 360 degrees, something like that.
Yes.
Okay.
So the hexagonal lattice, square lattice, and triangular lattice.
Okay. So that relates to the classification of 2D
Wallpaper group.
wallpaper group.
Yes,
Okay.
yes, yes.
Yeah.
So-
if that's Z5, then it will be a quasi crystal. Because pentagons don't tile to be a crystal.
Yeah. That's you're saying the pentagons
Don't tile to be a crystal. Like it's like C5 symmetry
yeah.
and translation symmetry are not compatible.
Okay.
So you take pentagons and then put one next to each other.
Then there will be a shift.
Yeah, there'll be gaps between.
Okay, I see. Thank you.
So yeah.
Yes. Yeah. On the other side, if you have immersion symmetry, which is P1 for the wallpaper group, you will also, after some calculation, you also have the symmetry indicator to be Z2, and that is exactly the Foucault Z2 unit. Okay, and this work by Po can be expanded to it can be very general. It can be expanded to 3D plane space group, or with time reversal and strong spin orbit coupling. But I want to note that there is still some open question on how this work related to K-theory on the tenfold classification, how it related to chirosymmetry or particle hole symmetry. That is still an open question for now. Okay. I want to thank you for your listening.
Okay. Thank you. John. Okay. Any questions? Any other questions? Okay. I have a question regarding the calculation. Yeah. Still. Yeah. Can you scroll back a little bit?
Yeah.
Where? Yeah, right here. So how does the symmetry indicator relates to the orbitals, the type of orbitals? For example, here you can put S orbitals or P orbitals on either A, B, C, D, or you can put D or F. Then how does that affect the symmetry indicators?
A D, okay. If you put a D orbital after C2 symmetry, does it gain a -1? I think, okay. So after 2 C2Z symmetry, it must go back to itself.
Yes.
Okay, so 1 C2Z symmetry must have +1 or -1 eigenvalue.
Yes.
So that is how I draw these two one-year orbital as an indicator. I think you can put.
Yeah. So if you only care about inversion, S and D are the same.
Yeah.
So because S and D are actually different, but if you only care about what happens if you rotate by 180 degrees,
Yeah.
then both pick up a sine of 1, phase of 1.
Okay.
So they don't change the class.
I see.
That is still E.
Okay. So that applies to F as well?
Yes, there is two, like S, D, all the.
S is antisymmetric.
Yeah.
So it's -1.
And
Oh, you mean F is?
I think
F and P would be the same.
Oh, I see. That helps.
so maybe this is not what is really physical there. This is just an indication of the parity.
Yeah. Then what about hexagonal lattice, or what would change in the?
The symmetry group will change.
Yeah, I mean.
So you will have C3 symmetry.
Yes.
But yeah, that will be a complication. Like in principle, you can have all sorts of symmetry. You can also have skew. You can have translational plus and rotational symmetry, which is non-symmetric. That will be another layer of complication that I'm not going to go into. You can see the paper.
Yeah.
Okay.
Any more questions? Do you want to see the previous slides? Then how much for recording? Okay, cool.
Okay.
Yeah. Okay, so if there are no more questions, let's thank the speaker again. And let's have pizza.
Okay.
All right.
Yeah, very nice. Very nice talk.
Thank you.
Yeah.